troubleshooting there. If you only take down one note, take down my GitHub there, these notes are up there. This is a bit of a brain dump, so I'm just going to quickly run through some theory, and you can run the commands and have a play around later. And the notes are on Simon's Miniconf site as well. We're going to be talking about your typical sort of enterprise LAN or LAN within your organization, so not long fat networks, not the internet. They've been covered by previous good LCA talks. And this is some low-hanging fruit that you can sort of apply in the real world to make sure everything's running well now. This talk's based on work done by John Maxwell, our principal software maintenance engineer, and myself. It's not an official Red Hat talk, it's just what we do day to day. So we're going to be talking about some good stuff to do. We'll talk about how this all works in the kernel, and we'll find some problems, and then we'll fix them. So good things to do. Make sure you've got a point or a level that you're aiming for, because you can just keep tuning and tuning and tuning. So you want to say, this is good enough, let's move on. Define a metric that's important to you or your business or your application you're running. This might be throughput, it might be how long an individual transaction takes, it might be how many transactions you can do over a period of time, sort of like IOPS. Get everything working before you start tuning it. As the saying goes, you can't polish a turd. You just end up doing the work again because it'll perform differently. If you can get a repeatable production workload and just blat that over and over again, that's the best possible test I think you can do. If you can't get that, then try and get a workload that behaves like your production workload. So same syscalls, same data sizes, and you've got a pretty good good yardstick to measure by there. Don't rely just on the benchmark tools, and we'll talk about that in a second. Record every little change you make and its results. Here's some NFS stuff I made up. So here I've made one change and recorded the results, and here I made another change, and then I recorded the settings that were current during all my tests. Now I know very clearly what combination of settings worked, what I did, and what the results were, so I can go back and apply the best results, or the settings that gave me the best results later on. Things not to do. Don't go and cargo cult some dude's sysctl.conf from the internet. He might be doing something completely different to what you're doing, and his settings just don't work for you. Many configs you see on the internet are like a decade old or more, and the kernel's changed a lot in 10 years. It just doesn't perform like it used to. There's different settings that work differently now. And some are just plain wrong. Definitely don't apply the vendor 10 gig docs word for word. Your system will perform worse than before. And again, don't rely solely on the benchmark tools. Nobody calls you up and says, mate, I'll give you $50 to run a sick iPerf. That's not what you're there for. Use them as a benchmark to make sure your networking is performing well to capacity, and then move on to that production-like test. So how does this all work? We'll move across this graph. A packet arrives in the ring buffer in the network card. That's a circular data structure. The new data overwrites the old. That's why we call it a ring buffer. When the packet's in there, the NIC generates a hardware interrupt. The kernel will stop a running process. We've got to copy all the registers off. We've got to build a new stack. This is like super expensive. We then run an interrupt handler, and we just turn that interrupt off, shut the NIC up, and then we do that expensive context switch in reverse. So again, another expensive operation. The kernel schedules what's called a soft-R queue, or soft-R interrupt handler. And that's what actually pulls that traffic off that ring buffer and then into the kernel. We run it through protocol stacks, Ethernet, IP, and so on. And we end up putting the data payload in a socket buffer, and that's what the application then calls the receive system call to get the data from the network. This soft-R queue is interesting. It keeps running while there's traffic on the network card. The idea there is to keep drawing that traffic off to stop the NIC generating that hard interrupt to avoid that expensive context switch. So that's something cool the kernel does for us. You'll see a lot of mention of this backlog in tuning that you find out about this. To be honest, the backlog is not used an awful lot these days. I would say don't worry about it and just move on from it. Another important concept we want to understand is NUMA, or non-uniform memory architecture. So back in like the Pentium 4 days, we had one or maybe two CPUs and some memory and a bus in between. And we doubled the speed of that bus, DDR2, DDR3, and so on. But eventually that became our bottleneck. So we've taken that notion of CPU and memory, we call that a node. And we have now multiple nodes in a computer, and there's a cost to travel between the nodes. So it's much faster to have all the stuff related to one CPU and memory happening in the one place than to cross a node and incur that internode penalty. NUMA can get super complex. There'll be a test on this one at the end. I'm just kidding. But this is some Intel examples of their NUMA architecture. So it pays to understand the complexity of this and how it affects you. You can use NUMA CTL to do that. Here you can see we've got some CPUs and RAM in one node, some CPUs and RAM in the other node, and our cost between them. This is a very small system, only 2 nodes. You can get 4, 8, 64, really big systems, so it pays to know how that affects you. Hardware, PCI Express can have NUMA locality as well. You can check that in sysfs. It can also not have NUMA locality, and that'll be a -1 in that sysfs location. So let's find some problems and fix them. Before the kernel even does anything, we can lose traffic in the network card. ETHTool will show you that. Each vendor has a different name for this. Look for like drop, discard, and so on. Exos, which is a handy collection of shell scripts, has a cool grep for common discards. Don't rely on the ifconfig drop counter. It's inconsistently updated, not reliable. You want to be using ETHTool to check this out. And there's a number of reasons why this can happen. We'll run through them. So we can handle those interrupts poorly. In proc interrupts, we've got an array of interrupt channels going down, and we've got an array of CPUs going across. And we want to spread that load. So, because when we're in that interrupt handler, we've turned interrupts off and we can't handle a new one. And if we forget that interrupt, or if we ignore it, then we might overwrite traffic in that ring buffer and it's just dropped, it's gone. So this is a bad example. We've got CPU naught handling all the interrupts you can see on the left there. And that CPU is going to starve for interrupt handling time. IRQ balance is how you will fix this up. You want 108 or later, or if you're using a vendor package, you want that commit. That's got some NUMA detection stuff in it. You can balance manually, then you need to worry about balancing them into specific NUMA node CPU. IRQ balance does all that for you. I just say run IRQ balance. And this is a good example. We've got our interrupt channels going down, CPUs across, and we can see each CPU is handling a different channel. Let's assume they're all in the one NUMA node. The number of queues, that's that number of interrupt channels. Modern network interfaces have multiple queues. They hash the traffic into those. That's how we scale up to 10 gig and 40 gig. Ideally, we want one queue per real CPU, not hyperthread. And ETHTool can let you configure this as well. This isn't an output from a command, it's just a diagram. It's a good example. We've got one NUMA node over there, we've got 4 real CPUs, and we've got 4 receive queues. Here's a bad example. We've got the same number of queues and CPUs, but we've put them in different NUMA nodes. So now we're going to incur that internode penalty, that latency in running this and copying stuff from the NIC to memory. So that's not a good setup. And this is also another bad example. We've got too many queues, so we're going to overwhelm those individual CPUs, and maybe they'll start missing interrupts. If you have bursty traffic, it comes in high spikes and low spikes, or if the kernel's not picking up traffic for reasons we'll talk about in a second, you can increase the size of that circular data structure, that ring buffer. ETHTool can do that. You can see the parameters there. This NIC can go up to 4096, but the current settings are, say, 256. You can put that right up to, say, 4096. Some NICs can go really large. The QLC NIC's like 16,000 or something. Stick it maybe 4096 as a maximum. Every network card works this way except the Emulex One Connects. You just can't change them. Another thing we can configure is offloading. So in our networking, we've got an MTU, and then we need to break traffic up to fit in that MTU at IP and at TCP or UDP layer. So we can do that on general purpose CPU, sure. But the NICs sitting there mostly idle, they're very powerful these days, and they've got ASICs in them that can do that stuff more efficiently. So we can ask the NIC to do that. So we just give it a big bunch of data and a few hints about TCP, and the NIC does the actual work. You probably want offloading on as much as possible. You don't want it on if you're doing, say, IP forwarding, like routing or vert bridging or switching. And if you are troubleshooting and you turn these off, things work, you turn them on again and it starts breaking, complain to your vendor. These NICs are like super expensive. The offloading should work when we want our offloading on as much as possible. If the soft IRQ isn't running, or how much it's running, we can observe this in ProcFS here in SoftNet Stat. Vertically going down, we have one line per CPU, and across we have a few columns. The first column is our total number of packets we've received on that SoftRQ, on that CPU. Second column is our backlog, which we're not going to worry about. And this third column is when the SoftRQ has ended, so it's picked traffic off the NIC, but there's still been traffic in the NIC. That on its own is not bad, but if you're getting lost in that ring buffer and this is happening, maybe you want to pick from the CPU a bit more. NetDev budget is the sysctl, the tunable we do that with. As you can see, the default's about 300. You don't want to increase this a huge amount because then the SoftRQ starts hogging CPU time and the application and the rest of the system doesn't get enough chance to run. So probably keep that under 1,000 or so. And lastly, as we get into our protocol layers, we can spend too much time there, and that can be another reason the kernel isn't picking out of that ring buffer. Look in netstat-s for collapsed and pruned. Collapse means we're getting rid of all the headers and little in-kernel data structures and we're packing stuff down. This is also a very expensive operation. It takes a lot of CPU time. A quick thing about netstat-s, a lot of things in here are symptoms of packet loss, like retransmit, slow start, and so on. These show you that packet loss is occurring, but they aren't the reason for the packet loss. Whereas collapsing and pruning meaning we just drop in the traffic on the floor and it's gone, these are definitely reasons for packet loss. We can stop this happening by increasing the size of that socket buffer where the data gets stored for the application to receive it. For TCP, these are our tunables. We have a minimum, a default, and a maximum. And the kernel's got a super cool feature where it will auto-tune between that default and that maximum depending on how much data you need. A good default is maybe 256K, maybe a vendor default. Definitely don't make it too large. You can tell, well, this auto-tuning stops working if the application is setting its own socket buffer size, and you can tell that's happening by running strace and looking for these set sockets for the receive buffer and the send buffer size. If that's happening, the application just gets what it asks for and that auto-tuning is disabled. A sensible default is important. You might have seen this blog from Cloudflare where they had a 1 meg default and they were getting these weird latency spikes every now and then. And that was just the kernel trying to allocate 1 meg of memory, and every now and then it would just have trouble doing it. So they knocked the default down or fixed. For things that aren't TCP, this is like ping and everything else. You don't want to set a large default either. I would say just mirror your TCP settings if you don't have any particular reason to change them. And these also act as a ceiling for TCP in the maximum there. So there's no use having, say, a large TCP maximum and a small not TCP maximum. Some TCP options. So TCP is so popular because when it was designed, it was made extensible and we can add these options onto it. One cool TCP option is TCP timestamps, and these are a nanosecond counter of when a packet was sent and received by a system. These allow TCP to do its bandwidth moderation better, and in the TCP header, we have what's called a sequence number, and this is incremented per byte of data sent. Now, 32 bits wide, that's 4.3 billion. We can send 4.3 billion bytes or 4.3 gig of data very quickly these days. Once we reach that 4.3 billion, we go back to 0, and when that happens, a TCP stream can hang. Modern TCP is pretty good at avoiding this, but it still can happen from time to time. This is called wrapping the sequence number. Timestamps help avoid that. TCP timestamps don't work with NAT. Any other time you probably want timestamps on. Another TCP option is selective acknowledgements. So with just plain old 1980s TCP, we send some data and we wait for an ACK to say, yeah, we've got the data. What usually happens is we send some data and we fill this TCP window. And if it's like, yep, I've received, oh, you dropped here, but I sent all this. I've got to resend from here, the drop point onwards. So I've got to restart the conversation halfway. SAC lets us send this much, and if we drop this much, SAC lets us say, no, I only missed this little part, just send me that again, and then we've got this straight away. Much more efficient. There's a bit of debate about SAC, which I'm not going to get into. We think it's really good, turn it on. An application can also be at fault. We'll look at that. New connections come in, and the application has to call accept, a system call, to start a new TCP session. If we get too many connections coming in, this is called a SYN flood. You'll see this with Netstat-S with a stat called a listen backlog. You might see SYN cookies being sent. So this might be a SYN flood attack, or it might just be a lot of new valid traffic. And we can increase the number of sessions we can accept at any given time with this listen backlog. SO maxcon is a kernel permitted maximum for that number of sessions we can have waiting to be accepted. It's just a kernel permitted maximum. The application still needs to ask, oh, can I accept more sessions? It's an example of how to do that in C and Java, and your application might even have this configurable like Apache does there with its listen backlog value. The application can just not be receiving data, so this is once the session's established and we're at that end of that diagram in that socket buffer. Again, you'll be looking for collapsed and pruned in Netstat-S. Check SS, which will show you your sockets, and you can see the stat receive queue there. That means there's some data waiting to be received. If you see one sample of this, so run it every second or something like that, you see one sample, that's fine. You've just kind of caught your application in the act of receiving data. But if you see that receive queue sit for a long time over your samples, once a second or something, or it drains very slowly, debug your app to look at what it's doing. And lastly, back to our NUMA affinity. We talked about it's more efficient to handle interrupts in the same CPU or same NUMA node as the device is local to. It's also more efficient to have the application on that same CPU, that we take advantage of CPU cache affinity. So here's a very basic example. We have node 0 over there with our NIC that's also local to node 0. We want our application over there. Node 1 can do other stuff. And you